Hey students, welcome to lecture number 9 of Linear Algebra 1. So last time we talked about subspaces. So if I'm in Rn, then a subspace of Rn is a subset U, which satisfied 3 properties. So one property was that the zero vector is contained in U. And also if I have two vectors, U and V in U, then also U plus V is in U. And then we also had, if I multiply with a scalar, then this was again in U. So we had these 3 conditions. And if these were satisfied, then U was a subspace. And then we gave some examples of subspaces, which were, for example, in R3 given by planes or lines. And then we saw that, for example, also the image of a linear map is a subspace and also the so-called kernel. So if I have a linear map F from Rn to Rm, then inside this Rm we had the kernel of F. So these were all vectors which get sent to 0 here. And then here in Rm we have the image of F, which is just the set of all vectors which we can obtain by applying this map F here. And these two were examples of subspaces. And also then we introduced the notation of the span of vectors. And the span of some vectors was just a set of all linear combinations of these vectors. And for example, we saw that the image of a linear map F, so let's say F, the matrix of F, is given by a matrix which has some columns V1 up to Vn. So it's a map from Rn to Rm, so this matrix has n columns. And then the span of these vectors is exactly the image, because if I multiply this with a vector, let's say lambda 1 up to lambda m, then the possible outcome of this multiplication of the matrix with this vector give all linear combination of these vectors. So then we could write that the image of F is a span of V1 up to Vn. So for example, in example 16, we considered the following linear map, which we denoted by G, and this was a linear map from R4 to R2 by sending a vector of size 4 to multiplying with this matrix here. So this then gave a vector of size 2. And then we calculated this image of this by just trying to solve this linear equation that this equals some y1, y2. And then we saw that there are no conditions on these y1, y2, so we could always solve this linear equation. And therefore we concluded that the image of G is just everything, meaning R2. So we can obtain everything here in R2. And with this new notation of the span, we can also write R2 as a span of the vector 1, 0 and 0, 1. Because any vector in R2 can be written as a linear combination of these two vectors. But also by this fact I just said before, the image of G can be written as a span of the columns of this matrix. So the image of G, without doing any calculation, we can just write as a span of the vector 1, 1, 2, 1, 0, 1, and 1, 1. But because both of them are the image of G, they are of course the same. So the span of these two vectors equals the span of these 4 vectors. So this raises the question, how many vectors do I actually need? So I can describe the image of G with 2 vectors, but I can also describe it with 4 vectors. And somehow this here is maybe a nicer representation because we just need 2 information, these 2 vectors, and then the statement is everything in the image of G can be written as a linear combination of these 2 vectors. But even though the calculation of this image here is quite simple because we just write down the columns here. But it seems like that here we don't really need 4 vectors because we can just write it down with 2. So the question is, how can we remove vectors here in a smart way. So for example, we see that 1, 1 here, for example, is double. So at least it's maybe easy to see that we can erase this one, but then we still have these 3. And this we want to discuss today, and this will have to do with the notion of being linearly independent, because the statement is that if I have 2 vectors like these, they are linearly independent, so I'm not allowed to remove one of them. But if they are not linearly independent, which is then called linearly dependent, then I can remove something. So we will see that these vectors are linearly dependent, which basically means that one of them can be written as a linear combination of the others, and then I can just kick this one out of the span, and I will not change the span. So we will see that we can remove something here, or we can also remove something like this, and then we will see that this span is still the same. Okay, but first we will do this lemma here, which gives a similar statement. Namely, if I have L vectors in Rm, and if the Lth vector, the last one, but we could choose any of these vectors, so if one of them is in the span of the others, then the span of all these vectors is the same as the span where I leave this vector out. So sum of the statement is if this VL is a linear combination of these, V1 up to VL minus 1, then I can remove this from the span without changing it. So let's prove this. So we want to show that these spaces are the same. So I will give them names. So this here I will denote by V, and this here I will denote by W, and we want to show that V equals W. And both of them are subspaces of Rm, and because in homework 6 you will show that the span of any collection of vectors is always a subspace. So we want to show that 2 sets are the same, and for this we want to show that one is included in the other and the other way around. So here this span is of course included in this one, because the span of vectors is the set of all linear combination of these vectors. So therefore any linear combination of these vectors is of course also a linear combination of these vectors, by just saying I forget VL. Therefore this one direction is clear, so we know that W is contained in V, and what we want to show is the other direction, that V is also a subset of W, meaning that any vector in V, so any linear combination of these vectors, can also be written as a linear combination of these vectors, assuming that this VL is in the span of the first L minus 1 vectors. So now let's take some V in some small v and big V. So because V is in the span of V1 up to VL, we can write, or maybe let's do it slowly. So because V is in the span, so if we have some V in the span of V1 up to VL, there exist lambda 1 up to lambda L, such that this V is linear combination of these vectors. Because this is the definition of the span, this is a collection of all linear combinations. But also this VL, the last one here, is in the span of the first. So because VL is in the span of V1 up to VL minus 1, this means there are some other numbers, let's say alpha 1 up to alpha L minus 1, with the property that this VL can be written as a linear combination alpha 1 V1 up to alpha L minus 1 VL minus 1. But this we can now plug in here. So instead of writing this VL, we can write VL as a linear combination of these vectors V1 up to VL minus 1. and therefore this arbitrary vector v in the span of all of them so can be written as follows. So now I can take this part here and plug it in there, but now I can remove this VL here and use this formula here. Yeah. Oops. And this should be a V, sorry. So this V, which is a linear combination of all of them, can now be written as a sum like this. But if we write this out, what is the coefficient of V1? Well, here we have lambda 1, and here we have lambda L times alpha 1. So the coefficient here is lambda 1 plus lambda L times alpha 1, V1 plus. And then the last one is VL minus 1. So here we have a lambda L minus 1 times lambda VL minus 1. Maybe we could put it here in between. So here we have lambda L minus 1, VL minus 1. And therefore here the last coefficient is lambda L minus 1 plus, and then lambda L times alpha L minus 1. So and these are just some numbers, and the statement is that this V is now a linear combination of V1 up to VL minus 1, and therefore this V is also contained in the span of these first L minus 1 vectors. And this is what we wanted to show, because we wanted to show that any element here, which is a linear combination of all of them, is already contained here in the space of all linear combinations of the first L minus 1. Okay. So this is this lemma, and now let's use this lemma to understand this image here of G. So so this is example 18. So for this linear map G, by definition, we have this matrix of G, and then the lazy way to write down the image is just to say this is the span of the columns of this matrix, which we have here. But now we can use this lemma to remove a few vectors, because we learned in the lemma if one of these vectors is in the span of the other, then we can just remove it without changing the span. So here we need to check which one we can remove. So clearly, for example, this 1, 1 is in the span of these three, because it's just 1 times 1, 1. So this we can kick out. But also, so here we want to use lemma 9, 1 now. We see, for example, that this 2, 1 is 2 times this vector minus 1 times this. So here we see 2, 1 is 2 times 1, 1, which is 2, 2, minus 0, 1. So this means that this here is in the span of 1, 1 and 0, 1, because it can be written as a linear combination of these two. And therefore, by the lemma, we can also remove this here, and also this. So therefore, this span of these 4 vectors, by this lemma, is just the span of these 2 vectors. But now we can also change this a little bit. Maybe this sounds now stupid, but we can make it bigger by seeing that by lemma 9, 1 again. For example, we see that the vector 1, 0 is also in the span of these two, because this is 1, 1 minus 0, 1. So therefore, we wouldn't change the span by adding this to this. So the lemma is not just for removing vectors, but we can also use it to add something without changing it. So the span of these 2 vectors is actually the same as these 3 vectors, because by the lemma this is in the span of these, therefore I could leave it out without changing the span. But now also we see that 1, 1 is of course 0, 1 plus 1, 0. So this here is in the span of these two, so therefore we could also leave it out, and in the end we get exactly what we want, that this is just the span of these two vectors, which is just R2. So this is somehow now another way to show that the image of G is just R2. But we will also see later that, already at this place here you could stop. We have two vectors which we will see are so-called linearly independent, and they span the space R2. But right now we need to use this lemma 9,1 here 3 times to see that the image of G is exactly the span of these two vectors, which give every vector in R2. But also at this here you could show that maybe every vector in R2 can be written as a linear combination of this, so at this point you could also show that this is R2. Okay, so but in general now we want to come to this notion of linearly independence, and therefore the general question is when are we allowed to remove vectors from the span, because we want to reduce the information to just to the necessary vectors. So if we have in the case before 4 vectors, we don't need 4 vectors, we just need 2 vectors. So in general the question is how can we remove vectors without changing the span. And this will be the case if the vectors are linearly dependent, then we can remove them. And this is defined as follows. So first we will define the notion of linearly independent. So if I have vectors v1 up to vl in Rm, then they are called linearly independent if this equation here, so this linear combination of these vectors, lambda 1 times v1 up to lambda l times vl equals 0, just has one solution. So these lambdas are again real numbers. And of course this has a solution by just setting all lambdas to be 0. But if this is the only solution, then these vectors are called linearly independent. But if there's another solution to this equation here, so if we can find a solution of this equation where one of these lambdas is not 0, then these vectors are called linearly dependent. Okay. And what this basically means, if vectors are linearly independent, then this basically means that I cannot choose one of them and write this in terms of the others as a linear combination. But this will be the case if they are linearly dependent, because if I have another solution to this, which is not 0, then one of these coefficients will be non-zero, and then I can put this on the other side and divide by this factor, and then I will see that this vector can be written as a linear combination of the other vectors. But let's first do an example for this notation. So the question is, are these three vectors linearly independent? So here we are in the case m equals 3 and l equals 3. So I have 3 vectors in R3, and we want to see if they are linearly independent. So what we need to consider is this equation in the definition. We consider the equation lambda 1 times v1 plus lambda 2 times v2 plus lambda 3 times v3 equals 0, and we want to find the solutions of this. We know that 0 is a solution, but we want to see if there are more solutions than just this one. And if there are more solutions, then these vectors are not linearly independent, because they are linearly dependent then. And first we can write this in a different way by using matrices again, and then we will see that this is basically just solving a linear equation. Because we already learned before that the linear combination of vectors can always be written as a matrix times a vector, where the columns of the matrix are given by these vectors, and the vector is just given by these lambdas. So we can write these v1, v2, v3 in a matrix and multiply it with the vector v1, v2, v3. So in our case, this is 1, 1, 2, 1, minus 1, 1, and minus 1, 5, 1 times lambda 1, lambda 2, lambda 0, lambda 3. And we want to see if this is 0, where by 0, as always, we mean the 0 vector. Because this is a vector, and if we ask this to be 0, then we understand that this 0 is a vector, which has just zeros everywhere. So we just want to solve this linear equation here. And this we now already did a lot of times. So how do we solve this equation here? Well, we just consider the augmented matrix with these entries. 1 minus 1, 5, 2, 1, 1 on the left side, and on the right side we have zeros. And well, in this case, how do we do this? Well, here maybe minus 1 there, and minus 2 times there. So the first one stays the same. 0. Here is a 0. So here is a minus 2. And minus 1 times minus 1 is plus 1. So here is a 6. 0. Here we have a 0. And minus 2. 1 minus 2 is, so 1 minus 2 is minus 1. And yeah, minus times minus gives plus. So this is 3. And here we have a 0. Okay. And now we can remove minus 2 times the last row from this row, and maybe also add 1 times this to this, and maybe in the end multiply this by minus 1 to get rid of this minus 1. So in this case we will get 1, 0, 2, 0, and here we get actually just zeros, and here 1, minus 3, 0. Yes, and then we could change these two rows to see that this is 1, 0, 2, 0, 1, minus 3, 0, 0, 0, 0, and 0. Okay, so this is the row-reduced echelon form of this augmented matrix, and therefore we can read off the solutions of this linear equation here by seeing, oh well, there's a free variable here, so this is not, we don't have a unique solution, and the solution is given, or the solutions are given by lambda 1, lambda 2, lambda 3. So the lambda 3 is our free variable, let's say it's t, and here it's plus 3 times t, so 3t, and here it's minus 2 times t. So in particular, these vectors are linearly dependent. So they are not linearly independent. Because I can find a solution, so I can choose some t here. So let's do this. So for example, for t equals 1, we get that lambda 1 is minus 2, lambda 2 is 3, and lambda 3 is 1. So this means that minus 2 times v1 plus 3 times v2 plus 1 times v3 equals 0. So now we have a linear combination of these three vectors, which is 0, where these coefficients are not all 0, and therefore these vectors are linearly dependent. So maybe here you can check that this is minus, so if you can take the test if I did it correctly. So if you add these vectors, you should get the 0 vector. Yes. Okay, and in particular we see that because this here is 0, I mean this here, everything is 0, we see that this v3, for example, can be written as 2 times v1 minus 3 times v2. So in other words, this v3 is in the span of these two vectors. And then we can use again the lemma, which states that the span of all of them, v1, v2, v3, can be just written as the span of the first two, v1 and v2, because the last one is in the span of the first two. And in general, if you have a collection of vectors and you want to see which of them can I throw out, like here, so this v3 doesn't really matter, so we can kick him out of the span without changing the span, then what you would need to do is you would try to solve this equation here. So you would write all these vectors in columns of a matrix and try to solve this equation. Then you end up in the row-reduced echelon form and see if there are free variables or not. So if there are no free variables, then you just have a unique solution given by all lambdas to be 0, and then they are linearly independent. But if you find free variables, then you have infinitely many solutions, like in this example here. And then here at the spot of the free variable, so this somehow corresponds to vector v3, you will be able to argue that you can remove this vector because this can be written in terms of the others. Yeah, but first let's continue here, because now we could also ask, are we finished here? Because now we have the span of these two vectors, but we might ask ourselves, can we also remove now v1 or v2 without changing the span? So maybe just the span of one of them gives already the span of this here. But in this case, we see that v1 and v2 are linearly independent. So linearly independent. Because if I would try to solve this equation here, so if I try to consider a linear combination which is 0, then I would do the same calculation as before without v3. So I would just consider the first two columns. So I would consider, well, maybe this is, so this would lead to this augmented matrix. And then doing the same calculations, we would see that in this case, the row-reduced echelon form looks like this. And here we see there's no free variable, so there's just one unique solution, namely the solution that lambda 1 equals lambda 2 equals 0. And therefore they are linearly independent. So this means I cannot write v1 in terms of v2. So if I would have a solution which is not 0, for example minus 1 times v1 plus, let's say, 3 times v3, then I could say, well, v1 is 3 times v2, and then v1 would be in the span of v2, and then I could kick out v2. But here we cannot do this, and therefore this is the final. So this is the answer. We can. This is somehow the smallest possible way of describing the span of these vectors. And so in this example, we can now summarize what we did in the following theorem, which is as follows. So if I have a collection of vectors, v1 up to vl, then the following three statements are equivalent. So the first statement is that these vectors are linearly dependent, meaning I can find a solution of this equation where some of these lambdas are not 0. Then this statement is equivalent that there exists a j. So one of these v's, so there exist a j's, such that this vj is a linear combination of the remaining vectors. like we did in the example where J was 3, so V3 was the linear combination of V1 and V2. So this is equivalent to being linearly dependent, and this is also equivalent to saying that the span of all of them is the same as the span where we just leave out this vector Vj. And these three statements are equivalent. So let's prove this. So we need to show all directions, so we need to show that if we assume 1, then we can imply 2, and if we assume 2, we can imply 1. But some of them we already saw. So for example, the implication that 1 implies 2, 2 implies 3. So assuming that 1 Vj is a linear combination of the others, this just means that Vj, so this another statement is, another way of writing this just means that this is in the span of all of them, without, where I have no Vj. So this is exactly this, because if Vj is in the span of the rest, then I can write it as a linear combination. And then the statement of lemma 9.1 was that I can remove this vector from the span. So this direction here is exactly what we did in lemma 9.1. And then the other direction, 3 to 2. So if this here is the case, if this span equals this span, why can I write a Vj as a linear combination of the others? Well, because Vj, so Vj is of course in the span of all of them, because Vj is in here. But if this span equals this span, then of course Vj can be written as a linear combination of these. So this I will not write here, so this is clear. And so now number 2 to number 1. So we want to show that suppose this Vj is the linear combination of the other vectors, then these vectors are linearly dependent. So all vectors. So suppose that Vj is a linear combination, so maybe let's do it here, of the others, meaning I can find lambdas. So here lambda j minus 1, Vj minus 1. Oops, here this is a minus, and here it's a plus. So it's just that I leave out the j part there. So if Vj is a linear combination of the other vectors, then what I want to show is that all vectors are linearly dependent, and being linearly dependent means I can find a linear combination of all of them where the coefficients are not all 0, but where the linear combination in total is a 0 vector. And to find this, I would just bring this on this side here. So this just means that I have 0 equals lambda 1 v1 up to, and then lambda j minus 1 vj minus 1. And now I have minus vj here plus lambda j plus 1 vj plus 1 plus dot 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 lambda l vl. So this is now a linear combination of all vectors. And here this part, this we could write as lambda j times vj, where lambda j is minus 1. So in particular, minus 1 is not 0. So therefore we have a linear combination of all vectors where at least one of them is not 0, and therefore all vectors are linearly dependent. And therefore statement 2 implies statement 1. And therefore, so here we already know 2 and 3 are equivalent, and we showed that 2 implies 1. So therefore we just need to show that 1 also implies 2. So for 1 implying 2, we want to show that assuming they are linearly dependent, then one of these vectors can be written as a linear combination of the others. So we suppose, or we assume, that that I have a linear combination, lambda 1 v1 up to lambda l vl, which is 0, where at some point, let's call it also j, we have that this coefficient is not 0, because this is a definition of linearly dependent. We can find such a linear combination. Then what we can do is we can bring this vj on one side, so we could write it as lambda j times vj equals the other vectors. And here I need to leave this one out again. But because this lambda j is not 0, we can divide by this lambda j. So I could divide. So let me copy this and put it here. So I could divide by this here. So each part here I can divide by lambda j. So this just gives new coefficients. And what we see here is that this vj is now a linear combination of the other vectors, which is exactly the statement of number 2. And therefore this shows that these three statements are equivalent. So again, usually you will get a subspace given by a span of something. For example, the image of a linear map can always be written easily as a span of just the columns of a matrix. And then you want to reduce the number of vectors you need to describe this span. And this you can do by this theorem, because you just need to check, are these vectors linearly dependent? If they are linearly dependent, then I can remove one of them. Then I have some remaining vectors, and then I can ask again, are these vectors are linearly dependent? So I can again use this theorem and check if they are, if one of them is maybe a linear combination of the others. Then I can kick it out, and at some point this is not possible anymore, and then the remaining vectors are enough to describe your span. And the reason why we are interested in this is because next time we will talk about the basis of a subspace, and the definition of this is exactly given by the following, namely that a basis of a subspace is given by a collection of vectors such that the subspace is the span of these vectors and that these vectors are linearly independent. So we cannot remove them anymore. And somehow the basis of a subspace as we can then see that that any element in the subspace can be written uniquely as a linear combination of these basis vectors. And this will have a really important application. And yeah, but this we will see next time. See you then.